Hello everyone, this is the first video of a series I'm going to create during learning quantum computing. So everything is from my notes. I would love to share my knowledge with you and my notes with you. So what if I told you that right now we are on the brink of a computing revolution that could change everything from how we develop new medicines to how we protect our online data? Or imagine trying to find one person in a city of million people with a classical computer, you'd have to check each street, each building one by one. But with a quantum computer, it's like being able to check every location simultaneously. Sounds impossible, right? Well, welcome to the world of quantum computing where the impossible becomes possible. Let's start with what we already know. Your smartphone, your laptop, and even the most powerful supercomputers all work the same way using bits. These bits are like tiny switches that can be either on or off, 1 or 0. Everything you see on your screen right now is represented by combinations of these ones and zeros. Text, images, videos, it's all binary at its core. For example, the letter A is represented as 01000001 in binary. When your computer solves a problem, it processes these bits one after another, like checking boxes on a very fast to-do list. Even the fastest supercomputer can only check one combination at a time. But what if we could break free from this binary limitation? What if instead of bits that are either 0 or 1, we had quantum bits, qubits, that could be 0 and 1 at the same time? This isn't science fiction, this is quantum computing and it's happening right now. Do you remember our city search example? While a classical computer would check each location one by one, a quantum computer can exist in many states simultaneously through a phenomenon called superposition. It's like having millions of parallel universes working on your problem at once. This is a famous logistic problem, the traveling salesman's problem. It asks the following question. Given a list of cities and the distances between each pair of cities, what is the shortest possible route that visits each city exactly once and returns to the origin city? Imagine a salesman who needs to visit 7 cities, as we can see now on our screen. This salesman wants to find the shortest route that visits each city exactly once and then returns to his starting point. This seems simple, but as the number of cities grows, the number of possible routes explodes. Why is it complex? Well, with 7 cities, there are 5,040 possible routes. For 10 cities, it's over 3.6 million routes. This exponential growth makes it impossible for even the most powerful classical computer to check every route. The number of possible routes for a traveling salesman problem with 7 cities is calculating using the concept of permutations. A permutation is an arrangement of objects in a specific order. But how do we do the calculation? So the salesman has 7 choices for the first city. After visiting the first city, he has only 6 choices for the second, then 5 choices for the third, and so on. This leads to 7 times 6 times 5 times blah blah blah, and we get 5,040 possible routes. This calculation is often represented using factorial notation, which is read as 7 factorial. And you can see that if we have 10 cities, we are going to have 3,006,028 and 800 possible routes. Please keep in mind that this calculation assumes the salesman must visit each city exactly once and return to the starting point. If these restrictions are relaxed, the number of possible routes would increase significantly. So adding just one qubit doubles our computing power. Add another, it doubles again. This exponential scaling is what makes quantum computers so revolutionary for specific types of problems. In the context of quantum computing, 2 to the power of n refers to the number of possible states that a system of n qubits can represent. Here's why. A single qubit can exist in a superposition of two states, often represented as ket0 and ket1. When you have multiple qubits, their combined states can represent the superposition of all possible combinations of those individual qubit states. You can see it on the screen. This exponential growth in the number of possible states with increasing qubits is a fundamental characteristic of quantum systems and underlies the potential power of quantum computers. That's why in a game with 4 cards where only one is queen, a classical computer needs 3 shots to find the queen, while a quantum computer with 2 qubits connected need only one, because if we have 2 qubits, we have 4 states. This is something that Dr. Dario Gil said at the MIT Venture Capital and Innovation during his talk back in 2017. Now that we understand classical bits, let's explore what makes quantum computing truly revolutionary, the qubit. And let's take a look of the sphere, because when we are talking about quantum computing, we also are talking about the sphere. Unlike a classical bit that must be either 0 or 1, a qubit can exist in both states simultaneously, as we already mentioned. This is magic, this is quantum mechanics. Think of a qubit as a point on a sphere. While a classical bit can only be at the North Pole, 0, or South Pole, 1, a qubit can exist anywhere on the surface. This gives us an infinite number of possible states, although when we measure it, we still get either 0 or 1. Here we need to take a pause and talk about the bracket notation and what bracket is, because we are going to use it all the time. Bracket notation, also known as Dirac notation, is a powerful and elegant mathematical formalism used to describe quantum states. It provides a concise and intuitive way to represent vectors, operators, and their interactions in the context of quantum mechanics. Bra is a row, so when we are talking about bra, we're talking about rows, and represents the dual vector of a ket. Mathematically, it's a complex conjugate transpose of the ket. Here we have phi, which is the bra corresponding to the ket psi. And this is how we can see it as a row. So ket psi is column, represents a vector in a Hilbert space, often used to denote a quantum state. Example psi represents a quantum state, and we can see that it is a column vector. And last but not least, we have bracket, which represents the inner product or dot product between two vectors. Now let's talk about superposition. Superposition is perhaps the most famous quantum property. You might have heard of Schrodinger's cat. The cat is alive and dead until observed. So Schrodinger said years ago that if we put a cat inside a box and also put poison in the box and close the box, the cat is both alive and dead. We don't know which one is correct because first we need to open the box and observe. Qubits work similarly, existing in multiple states until we measure them. But I love animals, so let's find another example. Okay? These plates are in superposition. My wife hates me for this picture. They are both broken and not broken until you open the door, until you observe, until you measure them. The Hadamard gate is a fundamental quantum gate and plays a crucial role in creating superposition. It acts on a single qubit and transforms it into an equal superposition of ket0 and ket1 states. Over here we can see that we have 50% possibility to have 0 get 0 or get 1. Okay, so the Hadamard gate is presented with the letter H, and you can see the matrix and bracket notation. Let's take a look now how it's done. We are going to use a simulator, and also then we're going to use IBM's quantum learning platform. So this is a simulator. I already put here my Hadamard gate. Let's remove it. It's nothing over here, 0 off, moving the gate. We have 50% to be 0 0 and 50% to be 0 1, and when we measure it you can see that the single line becomes double. Okay, so what's the difference in the number of lines in a quantum circuit diagram? It represents the transition from quantum information to classical information. Single line represents a qubit, which is a quantum bit. Qubits can exist in a superposition of states, meaning they can be both 0 and 1. Double lines represent classical bits, also known as bits. Classical bits can only be in one of two states, 0 or 1. When we measure a qubit, its superposition, as we did over here, its superposition collapses. It randomly assumes a definite state, 0 or 1, with a certain probability. This measurement process effectively converts quantum information into classical information, so from qubit to bit. The double lines after the measurement indicate that the outcome of the measurement is now stored in a classical register. This allows you to record and use the result for further calculation or analysis. Let's move to IBM's quantum learning platform. As you can see, we're going to use one qubit. So we get the Hadamard gate. We have two probabilities, 50% each. We can see it also here on the sphere. And now we're going to measure it. And it says that it has 100%. Why is that? Because if we come over here, oh, something's wrong over here, but okay. It has more probability to be a 0, so it should be up, not down, the sphere. Okay, that happens. Now let's move back to our talk. Now we are going to talk about the truly bizarre part, quantum entanglement. When qubits become entangled, they share a single quantum state. Entanglement is a mind-bending phenomenon in quantum mechanics where two or more particles become deeply connected regardless of the distance separating them. This connection is so profound that measuring the properties of one particle instantly affects the other, no matter how far apart they are. It doesn't matter if we have the two qubits one next to the other or one here and the other at the end of the galaxy. Entangled particles don't have individual quantum states. Instead, they exist in a shared, unified state. When you measure the property of one entangled particle, like its spin, the other particle's corresponding property becomes instantly defined, even if it's light years away. While the measurement outcome is correlated, no information can be transmitted faster than the speed of light. This is because you can control which outcome you'll get when you measure the first particle. This spooky action at a distance, as Einstein called it, is what gives quantum computers their incredible parallel processing power. A simple analogy, imagine you have two coins that are always flipped in the same way, both heads or both tails. These coins are entangled. If you flip one coin and it lands on heads, you instantly know that the other coin also lands on heads, even if it's on the other side of the world. Change one and you instantly affect the other regardless of distance. Two entangled qubits can represent four states simultaneously. Three represent eight. And the power grows exponential. Again, we're going to move to the simulator and then to the IBM quantum learning platform. So over here, let me remove everything. I'm going to put one Hadamard gate here, the other over here. Now we need to connect them. The CNOT gate is what connects them. And now we can measure them. Going to IBM Quantum Learning Platform, we can do the same thing. As you can see, probabilities are here and the sphere here. So we take one Hadamard gate and then the second one. You can see down here we have the two probabilities also in the sphere. Now we have 25% for each one, and let's connect it. And now we can measure it, and we have two options. Okay, two probabilities. So today we took a high-level overview of quantum computing, talked a little bit about Hadamard gates, superposition, entanglement, and that's it. All right, folks, another video in the books. Hopefully, you made it to the end. If you want to see the magic of quantum computing in action, on the next video, we are going to write code in Jupyter notebooks and compare simulations to real quantum hardware, giving you a better understanding of the challenges and possibilities. If you somehow enjoyed my video, consider subscribing for more wacky content. The subscribe button is somewhere around here, there. Thank you for watching. Take care. Bye.